Hi, thank you for coming to this presentation. Today, we're going to be talking about the new ACI Code 323, or the Low Carbon Concrete Code that was released last year. My name is Matthew Adams. I'm an associate professor at New Jersey Institute of Technology in the Department of Civil and Environmental Engineering. So today we're going to talk about low carbon concrete. What is it? Why don't we use it? A little bit about our policy landscape, and then getting into the code. So why do we need low carbon concrete? Well, construction and building materials account for about 11% of global CO2 emissions, and concrete is responsible for 7%. So concrete's really one of the highest embodied carbon materials out there. The majority of emissions really come from cement production and the scale of use. But despite that, we still need to work on reducing our global footprint and working to limit the continued impacts of climate change. So what is embodied carbon? Embodied carbon is a measurement of the greenhouse gases that are released through the manufacture, transport, and installation of a product or material. This is typically expressed as kilograms of CO2e, or equivalent CO2. And that is a value that's going to capture the normalized impacts of several greenhouse gases. So we're talking about things like nitrous oxide, sulfur dioxide, all of these carbon monoxide, all of these materials that create greenhouse effects when released into the atmosphere. We're normalizing those all down to the same damage that an equivalent amount of carbon dioxide would use. This is just an easier way to sort of look at everything. This kilograms of CO2e is often referred to as the global warming potential. When we're talking about embodied carbon, technically embodied carbon is looking at the amount of emissions associated with the entire life cycle of a product. So from the time raw materials are extracted up until it's disposed of. But when we're talking about low carbon concrete at the moment, mostly we're focused on the A1 to A3, or the upfront stage. And this is from raw material extraction up until the ready mix truck leaves the ready mix facility. And the reason why we're focused on this stage is because this is where we have good standardized tools that we can compare everything closely together. While we would like to consider the rest of the life cycle, the tools just aren't there yet. We don't have equivalent items to what we call something like an EPD, or Environmental Product Declaration, which I'll describe later on in the talk. In terms of concrete, the Portland cement is the majority of CO2 in most concrete mixtures, and that is really because the production of Portland cement requires a large amount of energy, and then also the breakdown of limestone, the calcination of the limestone releases CO2 into the atmosphere. We really don't have a good way yet to capture that CO2. There are a number of efforts out there across the world that are looking to retrofit concrete or cement plants to capture that CO2. But right now, they're still in sort of pilot stage, trial stages, trying to figure out how to do it and how to do it economically. But we do know that concrete has been labeled the most destructive material on Earth, right? We've seen this in the news over and over again. The reality is that concrete has a relatively low embodied carbon per unit mass compared to other construction materials, certainly less than steel. However, concrete's low embodied carbon per unit mass is sort of outshone by the fact that we make so much of it. The scale of production of concrete, it being the second most used material in the world, is so high that it really has an impact on the world. Um, in terms of how much we make in the US alone, we make enough concrete every year to cast 650 new Hoover dams. And the US is not one of the largest per capita producers of concrete in the world. And so we're not even at the high end of what could be cast each year. So what is low carbon concrete? Low carbon concrete is a performance requirement, right? This is not a specific concrete mixture uh, design. Um, it's a requirement that's set by your LDP that's going to be based on reducing your global warming potential below a certain threshold. So in order to do that, first we need to set a GWP benchmark. I'll get into this a little bit more, but a GWP benchmark is sort of an average global warming potential of all of your concrete in a set region. Once you set that target, your benchmark, you then need to set a target based on that benchmark. So the target could be to make sure that all your concrete is below that benchmark, make sure that it's all below 85% of that benchmark, or even if you're starting fresh and you're trying to get people used to the documentation, starting that at 120% of the benchmark, right? It all depends on what is important for your area and how quickly you think you can meet it. And then once you set those targets, you need to design your concrete to meet or exceed your desired global warming potential reduction. Excuse me. So how do we get to low carbon concrete? Again, this is a design goal. It's going to require creative solutions. There are lots of different levers and knobs we can hit simultaneously to reduce embodied carbon, but not all of them are going to be available to you. Some materials are available only in some locations. So, for example, LC3 or limestone calcine clay cement systems are available in much of the world, but we don't have them here in the US yet. We have quite a bit of fly ash here in the US, and that's not necessarily available in other parts of the world, right? So, what is available to you is going to be dependent on your locality, and then also what you can use is going to be dependent on cost and what sort of cost you can absorb. It also requires knowledgeable engineers, contractors, and laborers, right? We know that not everything is going to get treated the same in terms of getting the knowledge out there. We've seen this in terms of the local issues with Portland limestone cement that we've had here in the US as we've rolled that out. We've seen a lot of flat work that's had scaling. And a lot of that is really not because the material is inherently bad, but because we did not train our masons to place it correctly, to wait enough time for the bleed water to come out, etc. And so really we need to make sure that our training is not just with our engineers, but across the entire construction program. So what are the tools that we do have available to us? I'm not going to get in depth into all of the different ones that are available, but we can use what are known as lower carbon binder systems. So this is a really big range of things from completely non-Portland cement systems to things like LC3, which have a reduced Portland cement content, to just simply substituting some SCMs into the system. These all have a range of tools that we can use. We can also look at reducing our binder content, so lowering our total Portland cement or all of our cement content by increasing the amount of aggregates that we have. This requires you to have a better gradation of your aggregates, requires some engineering up front to understand your aggregate sources and what you can actually do. But that is a really successful way of reducing cement content and thus reducing your GWP. We can also use recycled materials. So these are quite popular, but not all of them have a high impact in terms of reducing CO2. It's going to be dependent on your location, where your processing facilities are, what sort of tools you have to process them. It's really highly location dependent in terms of whether recycled materials have a big return on investment for CO2 reduction or not. A couple of things that are sort of outside of those basic material options are going to be first looking at your specifications, updating them. You want to provide as much flexibility to the concrete producer as possible, right? The moment you start having prescriptive requirements for cement content, for what slump you need, etc., you're tying the contractor's hand behind their back in terms of giving you a lower carbon mixture, right? So if you think about your concrete specification, if you still have a slump in your specification, you need to take that out of there. Slump used to be a good indicator of water content and water to cement ratio. It no longer really is with the amount of admixtures that we have. Really, the slump needs are going to be based on the construction methodologies that are used. And so if you remove that requirement from your specifications, you're giving your contractors uh, the right ability to modify the mixture to meet both your GWP requirements and your placement requirements. Next is to design for durability. So even though I said most of what we're looking at is going to be about upfront embodied carbon, we always want to make sure that we're having our concrete last the longest it can. Um, and when I talk about durability, I'm not just talking about material durability, but I'm talking about use durability as well. We want to make sure that we're designing buildings and structures to be able to last in terms of needs for society, right? How many buildings are you all aware of that have been taken down, not because they were in poor shape from a durability material standpoint, but because they just no longer fit the use requirements? So we want to make sure that we're designing both for longevity of use and longevity of materials. And then finally, don't over design your buildings, right? Not everything we design is the Burj Khalifa. Not everything needs to be super high strength concrete. And even if you're talking about your normal strength concrete, I've seen a number of designs out there where you're ordering 25 megapascal concrete, and then on day 7, your concrete breaks are coming in at 40 or 50 megapascals. That concrete is over designed. You're getting too much strength too early. That means you have too much cement. We need to start thinking about ways that we can set upper quality limits to prevent too much cement from being put into a particular mixture. So that's just enough, sort of the range of tools we have available to us. I'm not going to get too far in depth. There are many other presentations available out there that get into how to use all of those tools. We're really here to talk about policy and code today. So why aren't we using low carbon concrete more if we have all of those tools available to us? What's stopping us? First, there's a fear of cost, right? And some of that is well founded. New materials that are not widely available on the market tend to be more expensive. Early adopters pay a little bit more, though we do see many companies, particularly private companies, that are interested in being early adopters as a part of marketing tools to the public. But really, the cost is not necessarily in the materials. Most materials that make it to full-scale production do so because they can get the cost of the material to be comparable to existing products. Really, the cost that we're looking at comes from the knowledge transfer. If you think of a design firm, right, they have an engineer learning how to use a new material, learning how to specify it, where they can use it. They're spending time reading, maybe watching webinars like this, and that's not necessarily time that they can bill to a client. So you're losing money there. When you're talking about new materials, sometimes we screw up with new materials. We see this with the Portland limestone cement or the rollout of that here in the US, where we're seeing a lot of scaling. Now we're having to replace or refinish those surfaces. That costs money. And so really making sure that we have a robust knowledge transfer system across the entire spectrum is going to reduce the costs associated with that. Next, space and capital is a real concern. I work a lot in the New York City metro area, and we see our ready-mix concrete facilities here are very, very small. They maybe have space for 2 silos and 3 aggregate bins, right? So they've got one with Portland cement in it, one with an SCM in it, and then their aggregate bins have sand and 2 types of coarse aggregate. If you want them to bring in a new material, they either need to build a new silo, which here in New York they really can't do. They don't have the space for it, even if they wanted to spend the money on it. But they also want to make sure that that silo is going to be able to be filled consistently. So you need a product that has that is being produced at scale to consistently maintain a silo at a ready mix facility, which requires quite a bit of material. You really need to scale up very quickly to be able to serve the population. Liability is also a concern. Every time we're moving to something new that people aren't that comfortable with, we end up taking on risk that we as engineers, don't want to take on. We're a very risk averse group of people, not just for our own financial stability, but also for safety reasons, right? The positive thing is that with most of our low carbon concrete tools, we're not looking at major structural failure, sudden collapse issues. We're really looking at durability and serviceability issues that can reduce the long-term performance. That's still important, but we're not really concerned too much right now about sudden collapse. However, that liability is still an important question. A lot of this can be solved with the right political will, right? So systems that can help fund knowledge transfer, systems that can help fund expansion of ready mix facilities, systems that help take on some liability or offset some liability. All of this can be done with the right political will, whether it's through forcing compliance by setting code and regulations or by incentivizing compliance by providing offsets for knowledge transfer or for building more facilities. These are all things that can be solved with political will. Of course, that's really going to be dependent on where you are. Here in the US right now, we don't have a lot of political will at the federal level to push these kinds of ideas forward, but we're seeing quite a bit in certain state level regions where people are really still dedicated to moving forward in terms of addressing climate change. So, what are codes? I know this seems like a silly question, but it's really not. Codes are actually somewhat complex, and understanding how we adopt them is a really important part of the process and for understanding the low carbon concrete code. So, we can kind of break down codes into three types of things, right? You have what are known as model building codes. So, this is going to be like the FIB code, ACI 318, ASCE 7. These are individual documents written by professional organizations. Just because they're written doesn't mean that they're required by law, but they follow a specific process that requires multiple steps, multiple levels of approval, open comment periods, and so that is a specific type of system. Once the model code is developed, then people can adopt it, but it's not adopted just because it's written. We then have things that are what we call amalgamations of codes. These are things like the International Building Code that we use here in the US. And this is a recommended set of model building codes. Really, it's just saying here are all of the codes that you should use together. And here are some caveats or changes that we would suggest going along with that to those codes. This makes it really easy for jurisdictions to adopt a set of codes without having to go through each one and understand it in depth. The International Building Code is really a set organization where they have a lot of input on what codes should be developed, and there's a whole process for determining what goes in there. Again, just because the International Building Code is published doesn't mean that it's immediately required, right? The codes that are required for you are what are known as your jurisdictional codes. What the jurisdiction is going to depend on where you are. But basically, it's whoever tells you what you need to follow in terms of building codes, right? So here in the US, we don't have a national level building code. Instead, each state sets their own code requirements. And in fact, in some states, it's set at each city level. It's a municipal requirement. So really, you have a range of different code options available to you across the US. In other countries, it may be a national level code or it may be regional codes, but it's going to differ depending on where you are. The jurisdictional code, however, is what is the law, what is required by law for you to follow. And so again, just to kind of push these two pieces apart, just because a code is written, it doesn't mean that it's a requirement. It's not a jurisdictional code. It's not a required code until it's adopted by legal policy, right? And so that is a directive set by your government, and adopting a code needs to come with enforcement requirements, and then the adoption also will accelerate change. In terms of Code 323, why did we develop the low carbon concrete code? Really, we needed to address an issue that was happening here in the US and that I think has really been happening around the world. Um, in lieu of codes being developed, but a need to push forward in terms of requiring reduced embodied carbon, um, there were a very broad set of policies and requirements set around the country. You can see here a map of the US. All of the different colored in states were places that either had approved or passed some sort of policy that limited the embodied carbon in concrete. And the difficult thing was that all of these came with very varied methodologies, different prescriptive limitations. Prescriptive limitations are really stifling in terms of innovation and change because you set them and they get stuck there and they don't always get updated. And in a lot of places, we had unrealistic or unattainable goals. And so we really needed a code to sort of set a standard that could be used across the country. Um, this meant including how do we benchmark, what types of benchmarks do we use, what limits should we use, how do we calculate things, because at the end of the day, all of these are requiring LDPs or licensed design professionals to determine and sign off on specifications and materials needed to meet compliance. And so we needed something that was standardized. So Code 323 was developed. This is the committee that developed it. I was fortunate enough to be chair of this committee along with my vice chair, Chris Ferraro, and our secretary, Andrea Shocker. This group of people worked very hard to get a code together pretty quickly. We published it last November, so it's been out for almost a year. And as far as we know, it's the first of its kind model building code developed in the world. It follows consensus process, meaning that we followed all the right rules for this to be considered an actual model building code. And at the end of the day, it provides designers with a set of global warming performance requirements, or a way of setting those global warming performance requirements. It's important to note that ACI 323 does not tell you how to make your concrete. It does not tell you what types of materials you can or cannot use. All it does is it sets your global warming potential performance requirement. And so that is going to give your engineers a tool to set into a specification that gives your concrete ready mix producer the right number that they need to hit with their available materials. Our framework for the code requires made us that we had to learn basic code terminology and language, right? This is a whole other language than writing a guide or other documents. And then we had to determine our methodology. So how do we divide things? What is the proof that we need? What sort of requirements should be met? And then most importantly, what were our exceptions? So what does 323 apply to? It applies to both new construction and repair and rehabilitation, really anywhere that you might use ready-mix concrete. Right now, we really only apply to ready-mix concrete. I'll get into why in a second. But in most cases, repair and rehabilitation will not trigger the code. The code is triggered off of the amount of concrete that will be used in a particular project. And so unless you have a really large repair project where you're using a lot of new ready-mix concrete, it's unlikely that you'll trigger it. The code does cover all different types of systems, so buildings, pavements, hardscapes, bridges, tanks, underground structures, basically anywhere where you would use ready-mix concrete, the code applies. So what are our exceptions? Our exceptions really were developed based off of where we had enough data in most locations to set a GWP benchmark. So right now, or when the code was developed, we really didn't have that information available for precast concrete, tremie, auger cast, and shotcrete. All of these are materials that have really specific requirements in terms of mixture design, but also are only used in specific applications that are often decided before we would get to the spec writing portion, right? And so without proper data to set benchmarks for those, it's really difficult to require them to follow a code, right? You need to be able to set a benchmark. We also don't cover pavers and masonry units. Unlike the other items, which we hope to add in the future, it's unlikely that we'll ever add pavers and masonry units because those are really outside of the scope of ACI. Um, and then it's important to note that currently we only apply to a certain design strength range. So again, design strength. And so this is going to be about 22 megapascals to 55 megapascals. We don't apply it to low strength and high strength concrete, again, because the data just isn't available there yet to set benchmarks. We're hoping in the next round we can start to require that as more data becomes available for benchmarking. So again, what is a benchmark? I've used this word a number of times. A benchmark really is a standard or point of reference against which something can be compared. So in terms of GWP, this is going to be an average global warming potential of the concrete that we're making today, right? We want to know what is the normalized GWP for us today. That value is going to be a moving target over time, right? As we start to use more and more low carbon concrete materials, we're going to see that GWP decrease. If our goal is to eventually get down to net zero GWP, we're going to want to make sure that our benchmark is updated and that our reduction requirements stay updated along with that. It's important to note that a benchmark is not a minimum standard. A benchmark is sort of the average that we're comparing against. So here in the US, we have one national level set of benchmarks that were created by the National Ready Mix Concrete Association. They were done by both at the national level and regional. We have a very large area of land here. And so, what is the benchmark for concrete in New York City is certainly not going to be the same as what the benchmark is in Los Angeles because the materials are different, the transportation differences are different, the environmental requirements are different. So it's important to think about regions. What we see here on the left is the table for the for the eastern region of the US. So again, we're ranging from about 17 megapascals up to 55 megapascals, and that's broken into 5 different brackets based off of class of concrete or range of strength. What we can see here is that that is going to be set to a certain GWP, and it's going to vary based off of region, as I said. What we give this as in the code as a benchmark that can be used. However, we recommend that all jurisdictions actually set their own benchmarks. So they should use local data, right? The regions that are set by NRMCA are actually still quite large. So for example, the Eastern region or the Northeast region covers from I think Philadelphia region all the way up to Canada, right? That's a really large area, and it's unlikely that the concrete made on the Canadian border is similar to the concrete that's made in New York City, right? The materials that are available are different. The distances things have to travel are different. So you really want to make sure that your jurisdictions are set to be reasonable and to have good local data. So for example, here we have an image of Japan. Japan's a relatively small area, but we have really distinctive areas that are going to have different concrete GWPs. So for example, Tokyo may have its own GWP benchmark in the Tokyo metro area, whereas we might have a GWP benchmark for the entire Northern Island where Sapporo is, right? So you want to kind of look at how your regions work and where the metro areas are, and really kind of figure out different jurisdictions to set benchmarks for as you're going through and collecting data. The code also does not set a requirement for reduction from the benchmark. The only requirement we set is if you are using those NRMCA values as what are shown here in this table. If you're using those values, the code says that you should have a 15% reduction from those values. And that number was developed based off of what we felt was achievable in most of the regions. However, if you don't have if you're not using those benchmarks, which you are unlikely to use if you're not in the US, you really need to set your own reduction that is reasonable and makes sense based off of your local jurisdiction. So what is our code process? So first you need to choose the type of building that you're using. So building, pavement, bridge, etc. Then your compliance path, which is going to be based off of the size of your project. And we have three paths. So you're either going to limit your GWP for the largest buildings. For mid-sized buildings right now, we require you to set your documentation, so calculate your GWP and your benchmark. And then for the smallest one, no action is needed. And that's really to make sure that we're not penalizing people who are building small structures while we're still all learning how to do this. So for example, for building requirements, the largest structures are everything over 4,600 square meters gross floor area. Mid-range is 460 to 4,600 square meters, and then the smallest ones are anything less than 460 square meters. Again, we are focused here on that upfront embodied carbon, and the reason for that is because we have the right tools. We don't have the tools for the rest of the life cycle. And when I refer to the right tools, I'm speaking specifically of what are known as environmental product declarations. And so environmental product declarations are going to be really what you need for your documentation. So beyond your benchmark, for each concrete that you plan to use, you need to get an EPD. And the EPD is going to give you a range of information about environmental impacts per unit of concrete, but most importantly, it's giving you your global warming potential. And that is the number that you can use to see if you're meeting the reduction requirements set through this document. So with that, I'll say thank you. If you aren't able to ask me questions today during the live session, you can email me at adams@njit.edu. Thank you very much.